Alright, so we're going to start with looking at a certain scenario. And I've given you the graph and also the data, and this is not why we need the calculators, but at least it gives us some numbers to work from. Alright, so the year of a record set in the men's 100-meter freestyle in record time in seconds is given in the table below. You'll notice X, well, I don't know if you can see it, it's so dark in your paper, but X is the year. So even if you can't see it on your table, maybe write X is the year. And then Y represents the record time. And X equals 0 corresponds to 1900. So you can see that if 1900 was X equals 0, then year 56 is 1956. Then 1957, 1957, 1961. You can kind of see it go up from there. Now, the scatter plot of the data is given below. So when we look at this graph, what's happening as the years progress forward? What's happening with the swimmers? Their times get faster because their times are decreasing. So that means they're able to complete it in a faster amount of time. So you'll notice that between, what's our highest? 55? 55.4 and 48.21 are the highest and lowest values. Is that a big time span? It's like 7 seconds, right? But for swimming, that's a huge time span. Shave off even a little bit of a second is a huge thing in swimming. So they're getting faster, but as you look at the graph here, what do you notice around this part of the graph? Like you're decreasing, 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 and then what's happening with these kind of?
They're starting to level off a little bit.
They're starting to level off a little bit. Now, before we flip the page and maybe answer questions there, just logically thinking about a human being swimming, do you think that there's a spot where they're not going to be able to go any faster? Like, is somebody going to ever be able to swim the 100 meters in 25 seconds? Probably not, right? Because right now, the fastest it was in 1994 was 48 seconds. And it took them that long, between 1956 and 1994, so 40-some years, to shave it off 7 seconds. And we're starting to see the graph level off, right? So, if you flip the page here, I'll flip the page here off. The question that results from a situation like this is there a limit to human athletic performance, or is there no limit? Okay, so I want you to take just a few seconds here on your own, and I want you to list several reasons why you think there is a limit to how fast someone can go, or why you think there is no limit. Like, give me some reasons on why or why not there might be a limit on how fast it can go. Not just in swimming, but really any human performance, athletic performance. We're going to share out. You could, but let's keep it as human athletic performance that's not that technology doesn't affect, yeah, based on what we know now. So I know there's like vitamins and different things that could enhance it, but like just straight human athletic performance. We'll start sharing out here in about 15 seconds. Emily, what was one thing that you wrote down?
I said the human body can only take so much, and you'd have to be like a perfect tech body, and you'd have many technological enhancements to get any faster. So there's obviously a limit.
Okay. Say what you said at the very beginning.
The human body can only take so much.
Okay. So human body can only take so much. Okay. Lena?
Oh,
What's another thing you wrote down?
yeah, I basically said that it can only push itself physically to a certain extent before achieving like an athletic plateau, maybe.
I don't know how many of you have seen or done like P90X. Okay, where the crazy toning guy is like muscle confusion, and that's what they're doing because you don't want to reach that plateau. That's just what made me think of that when you said that. But it's true that like if you just run all the time, your body gets to a point where like if that's all you're doing and you're not changing your activity at all, it does reach this plateau where you can't go any further or do anything more because your body's gotten used to it and kind of you're stuck there. So it does plateau. So we can put that. Human body plateaus after a while. That's why any professional athlete does lots of different types of workouts, not just one thing. Bless you. All right. McKenna. Anything else, man?
I said that there are things that people need to do, like breathing. Like if you want to hold your breath for like an hour, it's physically impossible because you need breathe.
So if they're swimming
Yeah.
or something.
And they have to come up for air, which slows them down.
That's true. Good. Need air, water, calories. So you can't just keep pushing it, pushing it, pushing it. At some point, your body's going to fail because it needs those things. Anything else that anybody wants to add? I mean, those are all good things, and it sounds like Nick.
Speaking specifically to the concept of time,
Uh-huh.
there's the possibility that it could possibly get faster, but eventually you'd have to get down to time, which is just physically impossible. You can't cover 100 meters in 3 seconds, and in order to get even faster than that, you have to go into negative time, which is quite simply impossible. Which means that there has to be a limit somewhere.
Okay. So there has to be a limit. To time. Can't go negative. Impossible to cover distance. Would you say like in 3 seconds? Yeah, so if we just looked at it from the time aspect, there is a limit to the time that you need to do. And Shane, did you have something else?
Like friction, because when the body moves, it has to overcome the friction from air or water, and the higher the velocity, the bigger the friction is, and there's a point that the human body cannot like overcome the friction.
Yeah, good. Really good.
Leave it to Shane.
Okay, so does it make sense if we say human body wouldn't be able to overcome the friction at higher speeds? Okay, so all those are very good reasons to say that there is a limit, right? There is at some point we're not going to be able to get any faster. Now they might keep shaving off like milliseconds as you go, and I should look up, I think I did last year, what the current fastest speed is because I think it is a little bit faster. But it's not going to be, probably going to be pretty close to what it is in 1994. So we're going to use the scatter plot that is here. to estimate, and I'm going to zoom in a little bit because I know the scatter plot on your page is, dark and stuff. But if you look at where the last point is right here. If based on this graph we had to pick a lower limit, meaning the fastest this person might be able to go, what do you think would be a reasonable lower limit? Right now the lowest value is 48.21. So based on the data we have right now on this graph, what do you think the reasonable lower limit might be?
45.
Maybe
Not even that far.
I feel
Like
46.
47.
46, 47, 48. Because look at your pattern of data. It goes from 55, and then within 5 years it goes to 54, and then within 10 years it goes down to 51.9, and then once we get to 85, then in those, that's a time span of almost 10 years, and you only go within a second, really, different. So you're not probably going to have any huge jumps after that point. We've had some big jumps up here, but then we're getting pretty nitty-gritty right here. So I would say probably either 48 or 47, somewhere in there would be a good lower limit. And we have to estimate, because just based on this graph, we have to go from this pattern. So on the back here, use the scatter plot to determine. So we would say maybe between 47 and 48 seconds. So if you determine the limit just from the graph, let me zoom back out. We have to look at the pattern and, fancy word here, extrapolate. What extrapolate means is to try to extend out. If we kept that pattern going for another 10 years or so, where would we be? And so you're kind of seeing this curve come down and level out. And so between 47 and 48 seconds is probably where we would be at. Estimate the record for a men's 100-meter freestyle in the year 2000. Well, we're not going to do that part actually, because I think we're going to do that down here. Okay, so a model for the men's 100-meter freestyle record time in seconds is shown by this function here. And I'm going to switch it to this one so it's a little bit clearer. So it's given by this function. Now this function was created by the data. So they took the data, they put it into a calculator or a computer system, and they said, okay, based on this data, make a function that's going to predict this type of pattern in the future. This is what they came up with. The same data pattern that we had on the first page is shown here, but now this function is graphed over it. So you can kind of see, does that curve follow the points pretty closely? Yeah, not every point is touching the curve, but they're all pretty close to it. So we're going to use this model to predict a reasonable record for a man to swim 100 meters in the year 2000. Now, on here I said, explain how you determine your answer. Well, last year we said plug in 100 for x. Why would we plug in 100 for x? What's my x, though, on the first page? Yeah, my x is years, right? And my years started in the year 1900. Well, if I want the year 2000, that's how many years? 100 years later. So we're going to plug in 100 into the function. Now, I'm going to save you some time here. When you plug 100 in for x, because this represents 100 years, you end up getting that value right there, 47.47 seconds. So was that pretty close to our estimation before? Yeah, between 47 and 48 seconds. Now, it predicted that based on the data that was currently given, but is that probably exactly what it was in the year 2000? Probably not, but that would be a good estimation of where they would be at. All right. So if you go to the next page here, do you think that the previous questions covered enough results to prove that there is a limit to how fast a man can swim 100 meters? Why or why not? We've already talked about, logically, why it would make sense that there's a limit. But mathematically, could we prove, based on this stuff here that there's a limit?
No.
Not necessarily. Why not?
Because it's still decreasing.
Because it's still decreasing. Like if we plugged in 200 or 300, would we keep getting lower and lower and lower numbers? Yeah. So mathematically, we had to use something to predict the future, but it's not going to prove that there's a limit necessarily. So to write that in a nice way, we might say, okay, it's not proven because the data from the function keeps getting smaller. Which, as the y values get smaller, what's happening with our swimmer? They're getting faster because my y values mean time. So by smaller, I mean that they're getting faster over time. And so we still could argue there is a limit in theory because of physical limitations. And that's everything we covered before. Okay. So how many of you watched the Olympics over the summer? So anybody watch the swimming? You know how when they're swimming they have that line that kind of goes in front of them? It's the world record. Yeah. So how many world records were broken? Was it broken every time?
No.
No. I think a couple of them were broken, maybe 2 or 3 of them. But yeah, they put that line there, but most people are behind that line. And that world record is like the data that would be on that front page. It's the fastest record of someone swimming. But there were times when that record was broken. So that would still say, maybe they were like 0.3 of a second faster. That's not a huge jump, but they still are faster. But it's not going to be. Nobody's going to swim like 2 seconds faster than the world record. You're like Superman if you're going to do that. But so we would still say that there's probably a limit. We're just not sure exactly what it would be yet. Because there's still people that are getting faster and faster. All right, so we're going to begin the second part of the discussion. We've kind of talked about it in this situation of somebody swimming. But we're also going to look at it in terms of just a regular function. So function we're going to look at, and this is why you have your calculators, is x cubed minus 1 over x minus 1. Now, the reason I put parentheses is because in your calculator you need to make sure you have parentheses around the numerator and denominator. Okay? So what I want you to do right now is after you write that down, put that into your y equals. Okay, and then before we graph it, so for right now just put it into your y equals, and we're going to talk through this little paragraph here before we get to graphing it. Or actually, we might not even graph it, we might just look at the table first. So how do we know, like if I tell you that this fraction is undefined, what does that mean about that fraction? What's on the bottom of that fraction? 0, because we can't divide by 0. So when a function is undefined, did you raise your hand?
No.
Oh, when a function is undefined, it would be where the function, if it's a fraction, where you're going to have 0 at the bottom. So if you look at that fraction that we have here, this function, what number would make the bottom 0? 1, right? Because if we plugged in 1, you'd get 0 over 0. But this is why we talked about the indeterminate form yesterday, because you're still technically trying to divide by 0, so that's not allowed. So we would say, at this case, where x is 1, that's where this function would be undefined. And why? Because you get 0 in the denominator. Okay. So if we were to graph the function, what would happen at that point? If your function's undefined, that means it doesn't exist at that point. So what would be present at x equals 1 in the graph? How do we show something that
Imaginary.
doesn't exist?
Circles.
Okay, so we have two things here that were said. Like in the actual graph, it might have a hole at x equals 1, because a hole in the graph would mean it doesn't exist there. Or the other way that you might see it is a asymptote. So you can see it either way. At that point, something's happening. Either you have a hole or you have an asymptote, but that shows on the graph that you're undefined. If we were going to look at the table of values represented by the function, what would the table look like? What would happen, like you've had this happen to you in a table, what happens if you put in a number and it can't punch it out?
Error.
It says error, okay, because it can't give you a number because it doesn't exist. All right. So the other questions we have to ask ourselves is what will happen to the values and the graph as they come closer and closer and closer to that undefined value. So what's happening to our function as it gets closer to the spot where it doesn't exist? Yeah, as it gets...
decreasing one.
Thank you.
Well, we'll see, because we're going to actually determine that last question by making a table. So I'm going to put 1 right in the middle of my table here, because I know that's my undefined. So if I plug this in the calculator, what should be the y value?
Error.
It should say error, right?
Oh, I put 0. That's not right.
Okay. Now, we're going to pick values to the left and to the right, and actually I have too many boxes here, that slowly get closer and closer and closer to 1. Okay, so what's a number that's kind of close to 1? Closer, think decimal.
1.1.
0.5.
0.5. What's a little bit closer than 0.5?
0.99.
Okay, that's close. But is 0.75 pretty close to 1?
Yeah.
Sure. 0.5 would also be kind of close to 1. A little bit closer might be
0.6.
0.9. What's even a little bit closer?
0.95.
0.95 or 0.99? What would even be a little bit closer? 0.999. Okay, so we could keep getting closer and closer and closer to 1 just by adding up 9s, right? So on the other side of 1, something that's really close to 1 would be might be 1.001. Something that's really, really close to 1 on the other side of it. Then what's a little bit less close there?
1.1.
1.1 or 1.01? 1.1, and I guess we could have kept this one. And maybe 1.25 or something. What I want you to see here is that as we're coming from the left and from the right, so where 1 is our focal point, as you get closer from both sides, your numbers are getting closer and closer and closer to 1. Kind of like when I was talking about the door thing and walking closer and closer to the door, you keep getting closer and closer and closer, but are we actually ever going to get to 1 if we're just looking at the left and the right hand side? No. All right, so we're going to look at our table to see what happens with my y values. So you should have your function in and then hit second and graph to go to your table. And then we're going to put in these values. So 0.75, 0.9, 0.99. Maybe just even put in 1. 1.001, 1.01, 1.1. Okay. So if we look at the y values, as your x values are getting closer and closer to 1, what's happening with your y values? They're getting closer and closer to what number? 3. Because it kind of looks like on this side you're almost to 3 here, and then you're really close to 3 here. So if we kind of pinch our numbers together here and come close, like the number that logically would go where that error is might be 3. Okay? So we would say, as our written explanation here, what's happening. Oh, and we should probably put our numbers in. So 2.3, 2.7, 2.97, and then we have 3.003, 3.03, 3.31. So, written explanation of how to interpret a table like this and a function like this is that there's going to be a hole. The reason I know that there's going to be a hole at 1 is, first of all, there's an error, so I know it either has to be a hole or an asymptote. And I know it's not an asymptote because what happens with asymptotes on your graph? Like with your tangent function, didn't it go like this and follow the asymptote up? It doesn't get close to a y value. It just follows the asymptote up to infinity, right? Well, that's not what I see happening with these y values. These y values are getting closer to a certain y value instead of getting really, 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 really big, like it's following an asymptote up. So I know that there's going to be a hole. There will be a hole in the graph at x equals 1. Now your calculator probably will not show the hole in the graph because your calculator graphs like little pixels. You know, it's not going to show every single little point on the curve. So usually we don't see the hole, but we know it's there because of the error. And then from the table of values, we can see that as x gets closer to 1, so from either side of 1 you're getting closer and closer. What's happening with our y values? It's getting closer and closer to 3. So we'll say y is getting closer to 3. I should say, and you might want to write this down somewhere, but I should say that when I say f of x and I say y, I mean the same thing. So f of x values up here are y values. They're function values, so y, f of x, they're interchangeable. Alright, so definition of limit. This is the very simplified version. This is the one that you need to know for sure. A limit is a single y value. The graph or table meets as x approaches c. Now let me talk about what that little phrase means, x approaches c. You have a bunch of x values here. But we've set it all up around what focal point? What's my focal x value? 1. So in this case, we're looking for the single y value that your table is approaching, or your table is getting close to, or your table is meeting. As your x gets closer to some specific, we're going to call c value, because it's your focal x point that you're looking at. So in this case, your x is approaching 1. So as your x's get closer and closer to 1, what y value is your function getting closer to? 3. And that's basically what we're looking here as a limit. So for limit notation, we kind of put it all in one phrase here. That should be an M. So it's LIM as x approaches c. So the limit as x approaches some focal x value that we're looking at. So in this case, as x approaches 1. Your function is going to equal some limit. So in this case, if we were to rewrite like our function up here, so an example of what we have up there, it's the limit as x approaches 1. What is my function? What was f of x equal to all the way at the very beginning? Isn't that your function right there?
Yeah.
Yeah. So we're going to say, okay, the limit as x approaches 1 of this function, x cubed minus 1 over x minus 1, equals, and what was my limit value? What was the y value that my graph or table was approaching? 3. And that would be your limit statement. And that kind of wraps everything that we just did up in one thing. So you know what your focal x point is that you're approaching. You know what your function is. And you know the y value that your graph was meeting at on either side. Okay. In words, this might be good for you to write down too. If you were to say this out loud, this is how you would say it. As x approaches c, f of x approaches L. Approaches meaning gets close to. So as x gets close to c, which is your focal x value, your function or your y values are getting close to some y value. So in this case, 3. Okay. We're going to look at 3 examples here, I think. How many examples do I have? 4? 5? 3. We might only do a couple.
In the paragraph on the first page.
Oh, did I skip something? Yeah, too many pages. Oh dear. I totally skipped that part. Sorry. Okay, we kind of talked through this yesterday, and that's why I forgot to review it. So, go back to the first page really quick, and then we'll look at a couple of examples. I'm not going to go through all of them today. Alright, so subject of calculus is the interconnection of 3 topics. I talked about it yesterday without reading ahead a little bit. Does anybody remember the 2 branches that I talked about? Derivatives and integration or integrals. Good. Okay, so 3 topics. So, derivatives. Okay, I am spelling that right. Integration. And what do you think the third topic is? Limits. Now, this class covers Calc AB, which is in college, which is the first full semester of a calculus course in college, so Calc 1, and then a little bit into Calc 2. So when you get into the later parts of Calc 2 and Calc 3, they talk about more than just these 3. They start talking about vectors and all this other stuff, but we don't do that. So right now our concentration are these 3 main things of calculus. Derivatives and integrals are the 2 main branches of calculus, or they are the 2 main branches, but they're both born out of the concept of limits. So I like to call limits my umbrella, and then derivatives and integrals are the 2 branches that are underneath the umbrella. But limits kind of covers both of them. Before we define a limit, which we kind of already did, in calculus I like to use a multi-representational approach. So we use graphs, tables, real-life applications, and functions. We kind of look at it all different ways. So today we're just looking at kind of graphs and tables to determine limits. And then the next standard covers more algebraic ways to look at limits. So if you'll flip a couple pages, we're going to look at example 1. Estimating a limit numerically, which means, when you see that word numerically, it means to use a table. And we're going to actually evaluate the limit as x approaches 2 of x minus 2 over x squared minus 4. And we're going to do this graphically and with a table. So, what you'll need to do first is go to your calculator and put in your function. So we're going to look at x minus 2 over x squared minus 4. And make sure you put parentheses around the top and the bottom. And then I do want us to graph this one. And probably the best window to start with is just your standard window. Which probably the easiest way to do that is go to Zoom and then go where it says Zoom Standard and just hit Enter. Hello, this is Miss Cross. Hi. Yes, yeah. Oh, great. I'm actually in the middle class Can I call you back in a little bit? Okay, so I'll call. I just need to make sure I verify your address and kind of tell you or give you like the options of when we can deliver to see what works best for you. So I will call you back in a few minutes. All right, thanks. Bye. Did I give you a good screen?
Zoomed in by accident.
Yeah.
It
Okay.
doesn't look anything.
So from -10 to 10, we're going to actually mark this, and this is what you're going to have to do on your own, like when you start doing some of these problems tomorrow. I want to see what your window is. Best way to mark it is just to mark left, right, up, and down. Because some of your windows might be different, and then I just know what you were looking at when you graphed. And then with your graph, does anybody have a line that's like connecting this piece? Okay, good. Sometimes your calculator does weird things, and what should be happening there is there should be an asymptote there, right?
Yeah.
Because if we think of what's happening with this function, there are actually two numbers that are going to make this 0 on the bottom. What are those two numbers? +2, -2. If I plug in a 2, it's going to make it 0. If I plug in a -2, it's going to make it 0. So when you look at your graph, it looks like there's an asymptote at -2. What do you think is happening at 2?
Leveling out.
Instead of an asymptote, it's going to have a hole. Because I know that 2 and -2 both make this undefined. So something has to be happening with the graph at those 2 points. But at -2, there's an asymptote. So even though it doesn't show here the asymptote like drawn in, I'm going to actually draw it in here. Visually, I can see that I have an asymptote there, but I'm going to draw it in. And then when you draw on your curve, I'm just going to show that at 2, and my graph isn't going to be perfect here, but I do want to show that there is a hole there. So I'm going to draw a rough graph of what the calculator is showing me, but I am going to draw a hole at 2 to show that I've thought through the two places where my function is going to be undefined. And so maybe we write that here. 2 and -2 make my function undefined. Okay. So if I'm looking for the limit value here, I have a graph, but I'm also going to use a table. Now, what's my C here? What's my focal x point that I'm looking at? 2. So I'm going to put 2 smack dab in the middle. And then I'm going to pick at least 2 or 3 values to the left and 2 or 3 values to the right, but they need to be really, really, really close to 2. So the easiest way to do that is just to start with 3 decimal places, so to the thousandth place. The really close number right next to 2 in the thousandth place is 1.999. And then one step away from that would be 1.99. And then one other step away from that would be 1.9. So we're just decreasing decimals. And then what's a really close number to 2 on the other side of 2? 2.001, and then 2.01 and 2.1. So we just kind of...
Do we have to have 7 values?
Usually it's good if you have at least 7 tocaf. And since we have our function in our calculator, it's easy to punch in those numbers. So 1.9 gives me 0.256. 1.99 gives me 0.251. 1.999 gives me 0.25. If I plug in 2, what should happen? Error. Okay. And then if I plug in 2.001, we have 0.249, 0.249. This was 99. Okay. And then 2.1. Now you should start seeing a pattern here. Okay. So if you look at your x or you look at your y values, if I had to fill in a number here, where this error is. Does it look like from the right and the left, as I squeeze my numbers closer to 2, are my y values getting closer to a certain single y value?
Yeah.
Like these numbers are getting closer to
Like 0.2.
0.25 though.
probably 0.25. Like this limit value here is not going to be something crazy. So if I look at my numbers, it looks like from both sides it's getting close to 0.25. Because if I round this up, I'm at 0.25, right? And this was at 0.25003 or something. So I would feel really good about saying my limit here, or the y value that my graph is approaching from either side of 2, is going to be 0.25. It doesn't matter that my function's undefined at 2, because the limit is what's happening as you approach 2. So as you get closer and closer and closer to 2, what's going on with my y values? So it's okay that I have a hole here, but that means as I got closer and closer to that value, my y's are getting closer to 0.25. So we would say my limit's 0.25.
Why did it illustrate 2 completely different functions though?
What do you mean?
The 2 on the
Oh, this here?
Yeah.
It's one function, but because at -2 you have an asymptote, it's almost like it's broken the function in half, or the graph in half. And so you have different curves. Like on the one side of -2, your graph is doing something, but it is one function. Yep.
Why if I have 2 an asymptote and 2 a whole?
This is why. Which we'll learn too, but you don't have to write this down because this is actually the next standard. But if you can simplify this, like this is the difference of squares, so we could factor that and make it x minus 2 and x plus 2, right? And look what happens. I can cancel out the x minus 2, which the x minus 2 factor on the bottom is what, like if I plug in 2, that would make my function 0 on the bottom. But now that I can cancel out, now if I plug in 2, I'm okay, right? Because then 2 plus 2 would be 4. So this is why you get a hole there, because you can cancel out the problem. And then you're able to plug in 2. That's why it's a hole instead of an asymptote. Because I can't cancel out the problem where now if I plug in -2, I'm still going to get 0 on the bottom. That's why it's an asymptote instead. So that's kind of jumping ahead of us a little bit. That's a good question. All right, let's look at another example here. I know. Okay. And this is not one that we're going to be able to graph on our calculator. We're going to find the limit as x approaches 2 of this piecewise function.
Oh, jeez. You better remember the piecewise.
Well, this one's an easy piecewise function to graph, because it's just 2 straight lines. Or 1 straight line, actually.
That does not equal.
Yeah. Alright, so we're going to graph this one by hand. Now, if you have the equation y equals 1, which is what this represents, that's just a horizontal line through the y value of 1. So this horizontal line exists everywhere except for what x value?
2.
2, right? Saying where x is 2, that graph does not exist. So what's going to happen is we're going to have this horizontal line through 1, but at 2 we're going to have a hole. So I'm going to graph this horizontal line, and then at 2 my graph doesn't exist there. At the x value of 2, something else is happening with my function. At x equals 2, what's my y value? 0. So actually at 2 here, I'm just going to have a point where my y value is 0 and my x is 2. Okay. And now we're going to look at this limit as x approaches 2. Okay. And I'm doing this on purpose. I'm using f of x and my function interchangeably here. In this scenario, my f of x is this whole thing. So So I'm just going to write f of x, so I don't have to rewrite the whole piecewise function. And this does have a limit. And we're not going to be able to really make a table for this necessarily, but we can actually use my graph, and we can definitely find a limit here. So what's my focal point? What's the x value or my c value that my limit's focusing around? 2, because it's saying is the limit as x approaches 2. Now, the limit value is my y value. So here's where x equals 2. What are my y values to the left and to the right of that point?
1 and 3.
What's the y value over here?
Oh. Wait.
What's the y value?
1.
Is it 1 for every single point over here?
Yeah.
Yeah? Okay, so what's the y value of every point on this line here? 1. So from the left and from the right, are you approaching a single y value?
Yeah.
Like, if we were to make a table of this, you would have 1.999, 1.99, 1.9, but the y value of all those points will be 1. And then on the other side, it would be 1, right? So if you had to fill in the spot in the table where the error is occurring, where that point is right there, what would you logically put? Maybe it'd be better if we actually did make a table. Let's make a table, because it might be better for some of us. And we'll cut it down to just a few values. Okay. So if I was to plug in 1.99 and 1.999, what would be my y value according to this graph?
1.
1. So 1 and 1. What's my y value at 2?
0.
0. And then 2.001, 2.01, what's my y value?
1.
1. Okay. Now, this would be the same thing as having an error there. We don't care what's actually happening at 2. We care what's happening as you're approaching 2. So logically, if we looked at this pattern, what y value should go there? 1. So we would say the limit as x approaches 2 of this function is 1. Again, getting at this concept that the limit is what's happening as you approach a number, not what's happening at that number. Does that make sense? Like up here, it didn't matter that this was an error. Because logically, we could see as you got closer to it, it should be 0.25, right? Here, same thing. I don't care what's happening at 2. A limit is what's happening as you approach 2. And as you approach 2, everything looks like it should be going to 1, not 0. So my limit would be 1. Okay. Now, I'm going to stop there with the examples. We're going to pick up here tomorrow. But before we go looking at the review, I want to show you a quick little video online that uses an example of 2 cars that will